This is AP Calculus AB, and in this video I'm going to talk about section 7.2 again, anti-differentiation by substitution, but this time I'm going to focus on substitution in definite integrals as opposed to indefinite integrals in the last video. So what we're doing here is kind of the same process as what we talked about previously in section 7.2. We're taking integrals that have integrands that are kind of difficult to deal with. We can't use our basic antiderivative rules, and we're trying to rewrite them in a simplified form. Typically, we're accounting for things that would happen with the chain rule if we were thinking of it from a derivative perspective. So the process for this is very similar. There is one slight thing that's a little different because we've got the limits of integration, but in a way, these definite integrals are actually a little bit simpler to do because we don't have to do all of the back substitution that we did when we had indefinite integrals. So you'll see that as we go through this. So I've got an example here that's worked out, and I'm going to go through a couple of these with you, but primarily this is going to be an opportunity for you to do some practice and check your work. So we've got this integral from 0 to pi over 3, and we've got the integrand tangent x secant squared x dx. So you can see the substitution that's been done here. They said, let's let u equal tangent of x. That means the du is secant squared x, and there should be a dx there. So secant squared x dx. Okay, so then at that point, everything's already there that I need to substitute in. So you can see pretty easily that secant squared, tangent is just going to be u, and secant squared x dx is going to be the du. But the thing that's a little bit tricky down here, notice these limits of integration have changed. Now, the reason they changed is because these values we started with, those were x values. We're rewriting our integral in terms of u, so we need the limits of integration to change to values that are going to correspond to what u is. Now, remember, we have this relationship. Any u value is equal to the tangent of the corresponding x value. So that's what's being done here. We're finding the new limits of integration. When x was 0, the u is going to be equal to the tangent of 0, which is just 0. So that's where the lower limit came from. When x is equal to pi over 3, if I plug into tangent x, tangent of pi over 3 is square root of 3, and that's where the upper limit came from. So this integral that I have right here is numerically equivalent to the one that I started with. So the nice thing about that is they're both going to give me the exact same value. So I don't even need to worry about anything with the x's anymore because I'm going to get the same end result from the integral in terms of u as I would have if I had done the integral in terms of x. So in the end here, you can see it's simple power rule, upper limit minus lower limit, we end up with 3 over 2. Now, I also showed you down here just so you could see if we had actually done this in terms of x, we would get the same thing, right? We substitute back in for x, for u, we get everything back in terms of x, we change the limits of integration back to the x values that we started with, and we get the same thing. But really, this process is completely unnecessary because I've already got that value without doing that back substitution. So we can save ourselves a little bit of work by not back substituting, and that would really be the way that I would prefer that you do it. Okay, so let's go through a couple of these. I just want to kind of walk you through the process, and like I said, primarily I'm just going to have you try a lot of these. Okay, so we've got an integral here from 0 to 1, x over x squared minus 4 dx. So hopefully you did enough of these with the indefinite integrals that you're starting to be able to identify the u fairly quickly. So here our u would be x squared minus 4. My du then would be 2x dx. Okay, so like we talked about previously, if I have an opportunity, like if I'm actually working on a piece of paper, a written test, I can save myself a little bit of work here just by writing my modifications on the given integral. So I'm going to change the x to be a 2x so that I have 2x dx showing up there, and then I put a 1/2 on the outside. So I haven't actually changed anything about the integral. I'm just writing it in a different form. Okay, so now let's do the substitution here. So this is going to become 1/2 times the integral. And I'm not going to mess with the limits of integration just yet, but this essentially becomes du over u, or 1 over u du. But now look at these limits of integration. My lower limit was 0. I'm going to plug into this expression, right? So 0 squared minus 4 is going to give me -4 as a lower limit. And then when I plug 1 into that expression, 1 squared minus 4 is going to give me -3. So now I've got a new integral that's numerically equivalent to the one that I started with. Now, notice over here, it says, be careful because the absolute value is important. And we talked about that a little bit last time, but when you're doing these definite integrals, it really becomes a big deal. So when I do my antiderivative, I'm going to get a natural log of u. And that's going to be evaluated from -4 to -3. Now think about if you didn't put the absolute value in there, you would have a log of a negative, which actually is impossible, right? That doesn't exist. But if you think about graphically what's happening with this integral, we have like a 1 over u, which is like a 1 over x graph. Well, there is area between that graph and the x-axis when we're talking about the values -4 and -3. So it doesn't make sense that it would be undefined. That's why the absolute value is there, because it's accounting for the fact that we do have a solution that could occur here. So in the end, when I plug everything in, I'm going to get 1/2 times the natural log of 3 minus the natural log of 4. Now, when you have these log solutions, we've seen this before, but it really shows up a lot with these integrals. These answers can show up in a lot of different forms. That's a perfectly acceptable answer. If this was a free response question and you gave me that as your answer, that's totally fine. We could also use log properties though, and we could make this 1/2 natural log of 3/4. That would be acceptable. We could make this 1/2 natural log, natural log of 3/4 raised to the 1/2 power. That would be acceptable. We could make this natural log of square root of 3 over 2. That would be acceptable. So there's a lot of different ways I can write my answer, right? That's kind of the main idea. And you have to understand with log properties what's equivalent. So sometimes when you're doing multiple choice questions, you're going to run into a situation where, like, for example, you get this answer, and maybe the answer choice on the multiple choice looks like this. You've got to be able to see that those are actually equivalent. So it's not just what we're doing with the definite integrals. There's also some little, prerequisite skills that come into play. The stuff that we talked about at the beginning of the year that you were going to need to know in this course shows up a lot when we have these definite integrals involving logs. Okay, so let me go through one more with you, and then I'm going to have you try the rest of these. So this one, they actually gave us the u. So we have the integral from 0 to 2, x e to the x squared. So they said, let's let u equal x squared. Well, that would mean my du was 2x dx, right? So I need a 2 here, which means I need to put a 1/2 on the outside. And then from there, when I do my substitution, this becomes 1/2 times the integral. E to the x squared becomes e to the u. 2x dx becomes du. Now, my lower limit, u equals 0 squared, is just 0. And my upper limit, u equals 2 squared, would be 4. And now you can see I've got a really simple integral here. I'd have 1/2. Antiderivative here is e to the u. I'm going to evaluate that from 0 to 4. And in the end, I'm going to get 1/2 times e to the 4th minus e to the 0. This is another one of those problems where I can write it in a couple of different forms. This would also be the same thing as 1/2 times e to the 4th minus 1. Or I could write it as just a rational expression, e to the 4th minus 1 over 2. All of those are equivalent. So again, kind of the same situation as the logs, where sometimes you're going to have things where, if you're working a multiple choice, the form that you choose matters. If it's a free response, again, any of those are equivalent, so it doesn't really matter. Okay, so I've got a bunch more of these. Let's see. I've got 8 more of these definite integrals that I want you to try. And you'll see as you work through these, some of them are going to involve, trig functions like we talked about the last time. Like this next one, I'll just tell you where to start with this one so you don't get stuck on the very first one. That cosine squared in the denominator is the same as a secant squared. And from that, the substitution becomes pretty obvious. But then you can see here, we've got another one where that's going to involve a log. I'll let you figure out that substitution. But you can see that a lot of these don't involve trig functions. But the main idea is I want you to get the process down and feel good about that. The most common mistake that people make when they're doing a substitution on a definite integral is they forget to change the limits of integration to be u values instead of the given x values. Okay, so I want you to pause the video, take a few minutes and work through the rest of these, and when you unpause it, I'll show you the solutions. Okay, so here is that next one. You can see that I recognize that there was a secant squared there, so my u is tangent, my du is secant squared theta d theta, which is already there. And so this integral gets rewritten as the integrand is u cubed du, and then remember though, we've got to change the limits of integration. Tangent of 0 is 0, tangent of pi over 4 is 1, and the rest of this is, fairly trivial at that point. Just use the power rule and then plug in your upper limit and your lower limit. Okay, so that's kind of the main idea. Now, here's the next one. This is another one involving a natural log. So I made my u 5 minus t, my du is negative dt. And so there's a couple of things that you can do on this one. First of all, I need to have a negative dt. So I put a negative there, I put a negative on the outside, so I haven't really changed my integral. I'm just writing it in a different form. But notice that when I change my limits of integration, when I do my substitution, I now have a situation where my limits of integration kind of seem backwards because I have a lower value at the upper limit than the value at the lower limit. But what you could do there, you could use a log property if you wanted to, and you could flip it around. You could just make that the integral from 2 to 4 of du over u. You'll get the same answer in the end. Your steps will be slightly different, but you'll get the same answer in the end. So you can see with the way I did it, since this negative is out in front, I had to be really careful and make sure that I multiply everything that I do by negative 1. So in the end here, this is one form of the answer, negative natural log essentially of 1/2. Or if I want to get an answer that doesn't have a negative in front of the log, I can move the negative up and make it an exponent. 1/2 to the negative 1 is 2. So again, a lot of little number operations with logs will show up when you're solving these questions out. Okay, so here's another one. Here I chose my u to be negative cosine theta. My du is sine theta d theta. So everything's already there that I need for the substitution. The only thing I need to remember is that I've got to change the limits of integration, right? So negative cosine of 0 gives me negative 1. Negative cosine of pi over 2 gives me 0. And then from there, the antiderivative is really simple. Plug everything in. And just like before with the exponential, there's a lot of different forms I can write my answer in. It doesn't really matter which one you choose if it's free response, but a lot of your questions will be multiple choice. So realize that sometimes just because your answer doesn't immediately look like one of the choices doesn't mean it's not right. Okay, so here's another one. We've got cosine x plus pi. Now, this might be one that you don't even feel like you need substitution on. And if you can do it without substitution, that's totally fine. But if you did do a substitution, here's the steps. Your u is x plus pi, your du is dx. And remember, your limits of integration have to change. So now I've got my integral from pi to 2 pi of cosine u du. Take my antiderivative, upper limit minus lower limit, I'm going to end up with 0. Okay, so here's another one. We had the integral from 1 to 4 of cosine of square root of x over square root of x dx. So maybe not quite as obvious with the substitution on that one. But if you think about it for a minute, you might see that the u is square root of x and the du is 1 over 2 root x. So I need a 2 in the denominator, which means I need to put a 2 outside the integral so that those two will essentially cancel each other out. And in the end, when I do my substitution, again, if I've done my substitution right, I should end up with an integral that's pretty easy to solve. And at that point, now I've just got an antiderivative of sine, and then I just have to plug everything in. It's pretty simple from there. Okay, now, I put this one in here on purpose because sometimes what happens is you get so stuck in a mode when we're learning something new that you forget to do the obvious first. So you might have looked at this one and thought about, okay, well, how can I even do a substitution here? And then you play around with it for a while. Well, the reality is we should always check first. Can you just take an antiderivative? Because if you can, you don't need to do a substitution. So in the end here, I didn't even do a substitution. I mean, you could do a substitution and say u is equal to x. But if you do that, all you're doing is rewriting the integral in terms of u, and it looks exactly the same. It's not simplifying anything. So just keep that in mind. on the front of your mind should always be the first check. Can I take the antiderivative? And then from there, if you can't, then start thinking about algebraic manipulation or substitution. All right, and then this last one, or actually, I guess we've got two more here. So this next one, we've got a 1 over x. So this one's pretty straightforward. Now, if you notice here, I put in an absolute value of u. So think about this. Do I need the absolute value of u in this case? Now, look at the domain that I have on the original integral, right? The original integral goes from 1 to 3. So do I even need to do anything with that? I mean, the answer is really no, I don't. And the other thing is, notice that I wrote my antiderivative in terms of u, because if I had done a u substitution, my u would be equal to x. So I just wanted to show you there that had I done a substitution and said u equals x, my du would just be dx. Nothing about that integral would change. But anyway, the main thing is I don't need the absolute value because I really do have a domain restriction here. I'm restricted from 1 to 3, which are positive values, and my log will be defined everywhere. So I could have left out the absolute value. If you want to put it in there every time so you don't have to stop and think about that, that's always a safe bet. But you don't always have to have it there. Okay, and then the last one here, we had the square root of x plus 2. This is another one where you may not even need to do a substitution. But you can see on this one, since we've got an exponent that's a rational exponent, the number operations at the end sometimes can get a little bit tricky. Don't forget when you're dealing with things like this, 4 to the 3/2 power, I can choose to deal with that rational exponent however I want. So I'm thinking of that as like 4 cubed, and then I'm going to take the square root. Well, I can do that in either order. So the easier thing would be take the square root first, because that's going to give me 2, and then 2 cubed is 8. So remember to do little things like that with your number operations, because you could always do 4 cubed and get 64 and then take the square root, but sometimes you're going to get large numbers and you want to be able to do these things in your head quickly. So try to choose the path that's going to make sense to you, but also that's going to be the easiest. Okay, so that's really it on the substitution problems. Now, you should be able to go back and finish that 7.2 assignment and go back and work those definite integrals. The main thing here is you want to get a lot of practice with these because we're going to see a lot of this. So do a lot of repetition. If the Math Excel assignment seems like it's not enough practice for you, you can always go back into the textbook and get a lot more practice questions there.